Right, we're recording. All right, so we have just this last week third test in finals week, I believe is Wednesday at 4 o'clock. When is the last day to submit homework and labs? Okay. So will be the usual rule for the stuff for test 3. That is that you should turn it in to be eligible for full credit. It should be turned in by 11:59 p.m. On the day of the test, which is not this Wednesday, but next Wednesday. So the material for test 3 is lab 9 A, B, and C, 10 A, B, C, 11 A, B, C, and 12 only has the one part, 12. So for those to be eligible for full credit, doesn't mean they'll get full credit, but to be eligible for full credit, they must be in by Wednesday, what is that, the 12th? So that day of the test. Old stuff is still eligible for 90%. So I try to make my grading scheme such that the sort of miracle comeback is possible. So that stuff is still worth 90. And the stuff that is the stuff from the most recent stuff can be turned in until I put in a grade. And I have to put in grades for seniors on a Tuesday morning after finals week. So I need things by sort of late Monday night so I can turn around a grade. And out of fairness, I try to get everything, try to treat the juniors and the seniors and the sophomores all the same. So I should get everything by Monday. So it will go down. I'll probably take it for somebody who's not a senior if they're turning it in after that, but it'll probably go down another notch. Right now, things are eligible for 90. Late things are eligible for 90. It'll probably go down so that it'll be worth something, but it won't be worth as much. What are we turning in for Unit 12? A picture of your sign. So I will do I already have some of them in. Some people already turned theirs in. So that's not what I want to do. I want to do this. So here's just the Word document just says paste screen capture of your sign. And then let me go back and open up mine. Yours has to be different from mine. So the thing I call test alphanumeric is just something you can play with to help you figure out how to make your sign. So you can turn this on and then flip various switches. So A is that top, that line across the top, and B is that line down the front. And then you can figure out what letters you want to. So if I wanted to make a 7, If I wanted, my sign was going to say drink 7-Up, then I would want to connect A, B, and C. Now let me show the, so that was the tester. And then here's my sign. I have the other one running, so I can't run this one. I have to turn this one off and then turn this one on. So my sign says help. So yours is not allowed to say help. And then just make a screen capture, paste it into the Word I need to edit, and then paste it in, and that's all you need to for lab 12. Is that a hex display in the center? It is an alphanumeric, not, oh yeah, that's one of them. So it's an alphanumeric com. So it's in the same place as the hex display, but so let's stop running, okay. And it's under display, and the hex display just has these 7 segments. The but this one has additional things. D, turn this now on. D and E and F and P is the period, 1. And so in the original thing, 1 was just one solid thing, but now there is 1 and 2, so that's broken into 2 pieces. H, so there are these diagonal ones that weren't in the other one. There's this middle one that wasn't there before. So there are these diagonals, L, M, and N. So there's the vertical diagonal. So the horizontal is broken up into 2 pieces. That wasn't true previously. There's a vertical through the middle, and then there are these diagonals. So it's not the same as the hex. So you can make more, there are more things you can light up, and so there are more things that you can make up, you can make. Okay. Can't make all the Greek letters, but you can make some of the Greek letters if you're into Greek stuff. Okay. So you'll see here, let me try to, so N and M and L and K and J and H and I mean B and C. So there is an E, and then you say what's connected. Oh, A, that was the top one, and D and E and F. So that's what I need to connect to make this E. And then you can come over here, not come over here, sorry. Come over here and see for the E, what did I connect? I connected the red is, so the black are these sort of grounded things, and you need to ground it for it to work. So this black stuff that you see in these letters is going to be there for every letter. And then the red is for the things that I want lit up in my particular sign. These resistors used to matter more than they do now. It used to, if if you didn't have any resistor, it used to not work because you were sort of burning it up. And now they're more lenient and they'll allow you to have the wrong resistance or no resistance. So I prefer if you had the resistance there, but it works without it. And so if you don't use the resistors, I'll say okay. If you connect too many things, you need to lower the resistance. So you see here when I'm connecting two things, I'm making it a 110, and this is 110 ohms, not kilo ohms. So these resistors are ohmic, are in ohms, not in kilo ohms. So they're not huge 220 kilo ohm resistors, they're small 220 ohm resistors. And when I connected one thing, I connected it to 220. When I connected two things, I made it 110. But again, as I say, these days, I made this long ago when the system was more sensitive. Now it's not as sensitive. If you just skip the resistors, it works. It should not, it would not work in real life, but it will work in the simulation. We're going to submit that along with the test and homework. It is a lab, so you are going to submit it, yes. With the test and the homework, hopefully you would send it to me long before that. The labs are really due long before the test. I allow you to give them, to take up until the day of the testing, even after the test, to do it. But so you can hold on to them until the test, but and I made up the rules, and that's within the rules, but it still drives me crazy. And don't ask me for a letter of recommendation if you're the kind of person who dumps a lot of shit on me at the last day, and some of you do, then I don't like it, and it's going to come out in a letter of recommendation that I write about you. So either change your ways or don't ask me for a letter, one way or the other. So yes, you can do it. No, you shouldn't do it. And some of you probably will do it. Okay. Questions? All right, so that's lab 12. I used to have you make a full, make a sign on the test. I probably won't do that because I want to sort of minimize with people who insist on staying at home. I want to minimize the amount of software that they have to use, but I'm not going to eliminate the amount of software they use. So I might say, here's my alpha tester, it's already built, and you just have to flip some switches and make some particular letter, make a Q or something like that. So I might, so you can't ignore it completely. It used to be fun. I used to have people make a sign on the test, and most people did well on that problem. It was sort of fun, but it takes some time. And so I might just leave it at make one letter on the circuit. Then you're not building a circuit, you're just flipping some switches. You have to be ready. There are going to be, for the inductor lab, there are going to be some circuits. So that's going to be like the circuits in the resistor network. In the RC circuit that I gave you on test 2, on the resistor network I gave you in test 1, I will give you an LC circuit or an RL circuit and ask you to do some analysis of it. So for the LC, that's the one that's periodic. I will ask you to measure a period, get the corresponding frequency, compare it to the theoretical frequency. For the LR, I will ask for the time constant. There's a time constant going up and going down. They're usually the same. We have not combined inductors, but we have combined capacitors and we have combined resistors. So I can say, oh, here were 2 resistors instead of just 1 resistor. Here are 2 resistors in series, or here are 2 capacitors in parallel. So I can put in some little throwback to you know, the get the equivalent resistance or get the equivalent capacitance, and then put that into LC or put that into RL circuit. So, but my point there was there's going to be some circuits which you will have to manipulate and look at the oscilloscope for and do the measurement, and also prove to me with the oscilloscope that you know what you're doing with the oscilloscope. So put the needles in the right place. You might have to play with the time scale to blow the picture up or shrink it down enough to see what you want to do and grab the right screen capture. Questions? All right, so that's 12. You make sign something that says something other than help, and screen capture, send it to me. That's lab 12. It's done. The one thing that we have not talked much about yet is the stacks. And so I want to talk a little bit about a stack, and then we can talk about the microcode of a stack if somebody asks. All right. Word. Okay. Okay. So let's talk about first RAM, which we're supposed to sort of understand. RAM, and RAM is random access memory. And what do we mean by that? Memory starts off the smallest possible unit of memory is a flip-flop. That's a single bit. And then we put a bunch of them together and we get a register. And so a register is said to store a word. It may be 8 bits or 16 or 32 or 64. So we have different size words. And then to have RAM, random access memory, we bring together our idea of register and our idea of a decoder. And so we have a bunch of, and I can't draw as well in this as I could on the board, but I'll make do. So there's a bunch of registers. I have some in here, some decoder. That looks terrible. Decoder. This is a register. And the register, the decoder connects to all of the registers. And then I put in here a, what is this? The MAR, the memory address register. So the memory address register talks to the decoder. And then the decoder picks one of the registers. So one of the registers gets picked. And so that is, of all the registers, that's the chosen one. That's what we mean by random access. That as far as the memory is concerned, now we are going to memory and we want our line of code, or we want the value of our variable. As far as we're concerned, it's not random. But as far as the memory is concerned, it's random. You can put in anything in the MAR, and that will feed into the decoder, and the decoder will pick out that register. And then you can go, the next thing can be any other possible address. So the addresses pop around, as far as the memory is concerned, randomly. It's not and random access is as opposed to sequential access, which means you have to go to the very next one. So if you have something like a tape, so certain things used to be stored on tapes. So I think there are still some places that store things on tapes, at least for sort of backup purposes. Then that is sequential. That there are, if you're in one location of the tape, then the next thing that you would go to would be the next thing on the tape. Now you can fast forward or rewind, but so you can go through the consecutive addresses faster, but you must go through the consecutive addresses in a tape. Whereas in random access, this use of memory address register feeding a decoder allows you to sort of jump around. So you can access any register. So maybe we should call it not random access, but any access. So instead of calling it RAM, we could call it AM or something. Nobody says that. That's just me being stupid. Okay, so that is RAM. That is, we can put anything into the memory address register, and the decoder will then point to it, and we can either write to that value or read that value. Okay. Just making sure nobody's trying to chat me. Okay. Doesn't seem so. Somebody needs to either speak or mute. I'm going to make you mute. Okay. All right. So that is random access memory. Now let's compare that to a stack. Okay. So in a stack, there is a stack pointer. And it points to the decoder. Decode. I still didn't make enough room for the R, decoder. And then we have our registers. So it looks the same, And the decoder connects to all of the registers. So structurally, it's very similar. And so the stack pointer tells the decoder to pick out one of the, and I'll pick this one this time, pick out one of the registers that we are accessing. So RAM and the stack look very similar. The difference is in MAR versus a stack pointer. The MAR gets written to, and any random thing can be in there. So MAR, we write to it. And it can then hold any value. That's the random access part, that it can hold any value and therefore point to any register. What does the stack pointer do? The stack pointer is more of a counter. So the stack pointer is not something I write to, but something that holds a value, then I can increment or decrement. So it's got a hold. It's a counter. But it can count up or down, so it can count either direction. But so it can, as a counter, it can hold a value. It can increment, and it can decrement. It can go up by 1. It can go down by 1. But I don't write to it. I don't put anything into it. It has some value. It gets set not by me as a coder or any code I write. It gets set somehow by the system. And then I can tell it I can tell the stack to do things. I can tell the stack over in memory, I can read and write. And I can read and write to any address because it's memory, because it's random access memory. So I can read, put values, I can take values out, not necessarily take them out, but see what they were. Or I can write, I can put values in, and I can do that at any address and in any order. For this, the stack pointer, the thing that's telling me what address, what register I'm dealing with is only allowed to change by 1. And then the reading becomes known as popping, just to emphasize this more limited access than a stack has. And the writing is called pushing. And when I push or pop, I change the stack and I change it by 1. And in one instance, I'm incrementing, and the other I'm decrementing. And so, like, it depends how you want to, you can operate it sort of either way. But let's say that we increment with a push, and then we will decrement with a pop. And so we will always stick to that rule. So there is this rule of this much more limited access in a stack. It obeys these rules that the register I point to is controlled by something, the stack pointer, and that does not change sort of as radically as does a memory address register. It goes up by 1 or down by 1. And that depends on whether we are pushing or popping. And so it will always, if I say push is increment, then push is always increment and pop is always decrement. So I'm never going to like read the same. I'm not going to read some value twice. I can't say read the value and then read it again. I sort of read it, then my access changes. And as far as I'm concerned, that value may still be in that register, but I don't have access to it. So once you pop, the value still may be written in the registers of the stack, but you don't have access to it because of you have these rules of very restricted access. And the rules of the restricted access are known as LIFO. That the last in is the first out. And that's what we're saying here with this stack pointer and incrementing and decrementing. So right now my stack pointer is pointing to this register here. Okay. And we have to do some fine tuning of our rules and find out, is that where the stack pointer is pointing? We have to make up our mind. There are different ways to implement it. We have to make up our mind. Is that the next open spot, or is that the last thing we wrote? So those sort of details, like at the hardware level, we have to figure out, and we've sort of come up with some rules, and we'll just sort of say these are our rules. When it comes time to sort of write the microcode, I'll just say these are the rules I'm using, and then you tell me the microcode of it. It's something at a high level you don't have to worry about. You know that there's a push, you know that there's a pop, and there's a stack pointer, but you don't have to worry the details of is the stack pointer pointing to something the last thing we wrote, or is it pointing to the next available empty spot? You don't need to know, because that's down in the sort of the level of the hardware. So we're like connecting to hardware in this course. So we need to make some decisions, some at least fake decisions, to get through this last lab or next to last lab. But you don't need to know. You just need to know at the high level that there are pushes and pops in a stack. Okay. So that's what a stack is. It looks an awful lot like RAM, but take away the RA part, take away the random access, and give us the limited access that is given by a stack pointer. So RAM is more general and you can do more with it, but there are times when the specific situation that you're dealing with can be handled, is nicely handled by a stack. And so we will talk about maybe two of those situations. Okay. Now you can build a system that has what we would call a physical stack. I can have a set of registers and a decoder, and they are attached to a stack pointer. That can be built in hardware. It can be built that way. When it comes time for us to do the microcode, we're not going to do it that way. We're going to say there's just some part of memory. So we're going to be over here with RAM, and there's going to be some part of memory that we're going to call the stack. And so there's just going to be one new box. So all this stuff, the decoder, the registers, that was all a repeat of RAM. And the only really new thing was the stack pointer. So again, this can be a whole separate physical thing, or it can just be some part of memory. And then when it comes time to write something in the MAR, we can be writing the stack pointer's value. And that's what we'll be doing. So, so again, there are two. So this is the difference between RAM and a stack. The RAM is more general. It has more capabilities. And we can have a separate stack that obeys only this rule, or we can have the stack as just some portion of the RAM. Questions? Okay. Now, let me do some more. Blah. Okay. So two situations in which you might use a stack. One is to do some calculating. So we saw in our architecture, let me pull out, let me do lab 11. I think, yes, that's the one. So we had this picture. Now you see down here, I've added a stack pointer. I didn't add a stack pointer and another unit called the stack. I only added a stack pointer. So the stack is going to be just some part of memory, like I was saying a minute ago. Okay. But now I want to make a point up here about the ALU, the accumulator, and the TMP. Remember that when we were adding two numbers, first we put the first number in the accumulator. That was the first instruction we had to map out. And then we put a second number in TMP. And then we added those numbers and got an answer and put it back in the accumulator. Okay. So that tells us that before we do any adding, we have to get the data to be added. So hardware, when you're dealing with hardware, you need the data first and then the action. So you don't need to know that you need to get the first number in the accumulator, you need to get the second number in TMP, and then you're ready to add or multiply or exclude it or whatever it is you want to do, whatever arithmetic or logic you want to do. But first you need the two pieces of data you're going to act on. Okay. So when you're doing a calculation, so we can write a calculation, then I want to add 4 and 5. That's how we sort of think about it, with the action between the two pieces of data, and that's known as infix. And that's just the way we were typically taught, like, okay. But if you were following hardware, what hardware needs to do, you would put in a 4, you would put in a 5, and then you would say plus. So you would give the data, and then you would give the action. That's how hardware wants it. It needs to know the two pieces of data first, and that's postfix. So, but and then we also know that in our normal way of infix, we have things like this: 4 plus 5, 6 times 4 plus 5, like that, something like that. So this says, the parentheses tell us I need to add 4 and 5, and then when I get that answer, multiply it by 6. So infix sometimes needs parentheses to get the order of operations, to get the precedence correct, needs parentheses. Right. But there's a way to do, for it to do postfix. Proper postfix will have no parentheses. You would say 6, 4, 5 plus star. So you would see the data. It doesn't have to be all the data, then all the operations, but in this example, that's how it turned out. But I see the 6, and I'm not ready to perform an action on it. And then I see the 4, I'm not ready to perform an action. I see the 5, oh, now I'm ready. Now I have the data to perform my addition, which is what I'm supposed to do first. And then when I have that, I can then multiply it by 6. So I put the multiplication. So I keep the order of the data intact, and I move the operations to the place where I'm ready to perform that. And so this is the postfix way of doing that calculation. So instead of parentheses, you just put the symbols in the order in which you're going to perform them. And so sometimes you end up with a big string of data before you come across any operations. And then the way you perform this on a computer is with a stack. You put a 6 on the stack. Then that's the first number. Then you put a 6 on that 6 is on the stack, and then you push a 4 onto the stack. And then you come across the 5, and you put a 6 and the 4 and the 5 on the stack. And now you come across an operation, and you take the 2 things from the top of the stack. So you are popping off the 5 and popping off the 4 and performing the addition plus. So that would give me, and then you take that answer and you push it onto the stack. And that meant that I was here at this plus, and now I'm doing 6 times 9, and that will be 54. So one place that you can use a stack is to perform sort of operations that are given to you in postfix, because postfix supplies it the data and then the operation in the correct order for performing calculations in hardware. Hardware up here says, I don't know what the hell you're talking about. It says 4 plus. Plus takes 2 pieces of data. What are you talking about? 4, 5 plus says, here's a piece of data, here's another piece of data. Oh, here's what I do with the data. So hardware likes postfix. And if you have a complicated postfix, then the convenient hardware setup for calculating it is a stack. Okay. So that's the easy one. That's the easy thing that I'm not going to do. If I were in architecture, I'd do it, but I'm not going to do it here. I'm going to focus on the next one. Okay, so that's one place for a stack. Okay, let me show you another place for a stack, and then we'll start talking about the microcode of a stack. Okay, I'm going to, where's my clear? Okay. All right. So here is a coding example that uses a stack. So I have my main program. And somewhere in this line in my main program, I call a subroutine. So let me call subroutine A. I'll call it sub A. So subroutine is also code. So this code is somewhere in memory. So then when I come across here, there's another part of memory. I'm going to draw it as a different box. And here's subroutine A. And so this sends me down to this other part of memory. So that's what this does. And somewhere in subroutine A, it calls subroutine B. So here's subroutine B being called. So that's a different part of memory. So these are just different parts of memory. So here's subroutine B, another part of memory. And it doesn't call anybody because I'm tired. But at the end, it says return. So subroutine B does whatever it does and it returns. It returns, let me switch colors. So subroutine A called subroutine B. When subroutine B is done and it returns to subroutine A and carries on until it reaches, let me go back to blue, until it reaches the return of subroutine A. And then that returns to the main program. Okay. So one is I need to remember this. I need to get back there, so I need to remember. And I also need to remember this. I'll say, also remember this. So there's a sequence of things I need to remember in order to go back. So and now where was this? I say I need to remember this next line of the program. The next line of the program, remember our architecture, the next line of the program is the program counter. So I'm storing the program counter. Program counter tells me the next line of the program if I'm going through in a normal fashion. I'm not going through in a normal fashion, I'm jumping around, but I want to come back. So I need to remember what was the next line of code, and the next line of code was going to be told to me by the program counter. So instead of going there, I need to remember it. So I need to store the program counter. And then now my program counter is where I am in my code. Now I'm in subroutine A, and I come across this call subroutine B. Now my program counter is pointing to this line here. And so once again, I have to store the program counter. So this thing I need to remember is always in this calling of a subroutine is the program counter. It's a terrible looking P. So I've got to store the program counter. Okay. Then I come here to subroutine B and I'm executing code, executing code. Now I want to return. I want to take this program counter that I remembered and put it into this stored value of the program counter and put it into the program counter. And that will allow me to get here. So now I'm going to use this to get here. And then I'm going to use what I stored up here to get back here. Okay, so what is the purpose of all these crazy boxes? We see that we've stored the program counter more than once because we have a main program, it calls a subroutine, the subroutine calls another subroutine. We've at least twice here called the subroutine, and therefore stored a program counter. And then when it comes time to return, we take the last one. We take the last stored version of our program counter, and that's where we go back. So subroutine B returns to subroutine A, and subroutine A returns to me. That is, drum roll please, LIFO. The last value of the program counter that I stored is the first one out that I use to return. So having a subroutine, call another subroutine, that follows the LIFO protocol. That follows the protocol of a stack. If you've programmed, some people are IT, they haven't programmed as much, they've done more scripting than programming, but if you've done any kind of in-depth programming, then you've had plenty of subroutines calling other subroutines, and sometimes you even had a subroutine call itself. What's that called? Recursion. And you know that it is a very powerful method to solve a lot of important problems. And so if you didn't have a stack down in the hardware, doesn't have to be a hardware stack, can be just a little stack pointer that we're going to add. But if you didn't have this ability to perform stack-like operations, you couldn't have multiple subroutines, let alone have recursion, which is the way that so many problems are solved. So we have to have it. We just have to have it. Okay. So so now I've said, okay, there's a reason for a stack. Okay. Now let me just throw out a word there about the use of the word overflow. Okay. So we've talked about an overflow when we were dealing with numbers. We said, I have two numbers, I'm going to perform an addition. I have, I don't know, 32-bit numbers, and I'm going to add them. And then I might end up with a number that 32 bits is not big enough to represent. And we call that overflow. And that is indeed a type of overflow. There is a different type of overflow. We said here that we're just going to partition off a part of memory and call it the stack. And then with all these subroutines calling subroutines calling subroutines, especially if it's recursive, we don't always know how many versions of subroutines are going to be called. And we have only designated so much space in memory to be the stack. And so if we use up more memory in the stack than we set aside for it in the beginning, then we have stack overflow. That's a different kind of overflow. So occasionally I've asked way back when in unit 1 or something about overflow, and somebody gets a hold of the internet and just starts telling me all about stack overflow. We weren't ready then to talk about stack overflow. Only now are we ready to talk about stack overflow. And that's all I'm going to say about it, is just mention it. It's a different type of overflow. Okay. Both overflows are, I don't have enough units for what I need. One is I don't have enough bits to represent the number. That's the overflow we've known since unit 1. And then this is, I don't have enough registers designated in my stack to do all my subroutines, calling subroutines, calling subroutines. Okay. All right. Now we're going to talk about this as microcode steps. So basically do lab 11B. Maybe I'll do 11B part 1 and leave the other one. This is just some vocabulary. Okay. And then we're going to do this subroutine call. So I'm telling you what a subroutine call is. I'm going to do my little snip of this so I can draw on it. And then I'm going to put this over here, not up there. No, I don't need this. Okay. So I start with 4. Why do I start with 4? The first 3 steps are always the same. They're the fetch, so they're the same. So I'm just going to write same as before, or aim as before. All right, same as before. Befro, I can't do anything right today. Okay. Okay. So this is the same as before. And this is, I'll say ditto and ditto. Okay. That's the fetch cycle. It's always the same. We talked about it in detail at least twice, and I'm tired. Okay. But when we said last week, I guess on Wednesday, when I was rattling on about it, doing it for the second time in gory detail, I did warn you that a stack pointer is an awful lot like a program counter. You saw that in like the first picture I was drawing. They were playing the stack pointer in the program, and well, I was making the stack pointer look like the memory address register. But one of the things we feed into the memory address register is the program. So the stack pointer is going to be sort of somewhere between a program counter and a memory address register. Okay. So Assume that the stack pointer holds the last location of the stack, a designated portion of memory that was written to. So it already has something in it. In order to place a new value on the stack, we are going to, it's a subroutine call. We are going to store the program counter. We are going to push. We are going to write. And so we are pointing, I said here, assume that we're pointing to something that was written to. And so I want to write something else. And I don't want to lose this thing that's already written, or I won't be able to get back. So in order to get to the spot where I can write, I have to increment the stack pointer. This is where the stack pointer is like the program counter. We tell it to increment, it knows how to do that. So what are we doing down here? Control, control, control. And this one takes 7 steps. So it's control, control, control. And it's IR, IR, IR. Because it's the fetch cycle, so I need the instruction register to tell me what I'm doing. And then what is it? It's the stack pointer. And down here, in terms of arrows, I guess I'll say 14, 14, 14. That's just my setup. I don't have to think about that. Now, back up to 4. The stack pointer holds the last location that we wrote to. We want to write to a new location, so we'd better increment the stack pointer. The stack pointer is like the program counter. It knows how to increment. So it's involved, it has an action, but we need no bus. And we need nothing other than 14. That was 4. Increment the stack pointer. It's like the program counter. It knows how to increment. We just, control just needs to tell it to do it. IR tells us that we're doing a subroutine call. Control then knows what to do, and it tells the stack pointer to increment. Step 5. The stack pointer value goes to the memory address register. So again, the stack pointer is acting like the program counter here. It's going to point to a place in memory. That part of memory is known as the stack. The stack is just part of memory in this architecture. So the stack pointer tells us where that is. So we're going to jump to that part. And so we need to put that in the memory address register. So place the stack pointer's value in the memory address register. So that's going to be a 36. What color? Red. So that's going to be a 36. And who's doing something? The stack pointer is going to the memory address register. Who put their stuff on the bus? The stack pointer. Who took their value off the bus? The memory address register. That was step 5. The stack pointer's value into the memory address register. 6 says we are trying to store the program counter. So it says push the value of that when we're writing to a stack, it's known as a push. But you can think of this as just write. Write or store or push the value of the program counter onto the stack. So I'm taking the program counter and I'm writing it into memory in the part of the memory known as the stack, which now the memory address register is pointing to. Again, remember when we're dealing with memory, there's the 2-step process. Here's step 1. It happened to be step 5 this time, prepare the address in the memory address register. Then the next time we're dealing with the data, who's involved? Just the program counter, memory data register, the memory, which I'm going to call RAM, and the memory address register. Who put their value on the bus? The program counter. Who took their value from the bus? the MDR. This is the first time we've written to memory. Last time when we were doing lab 10, it was 2 reads. We read value, then went to the accumulator. We read a value, then went to temp. Now we're writing. This is the first time we're writing. So we're doing this 11-8 direction instead of the 9-10 direction. All right, let's get the arrows in there. There was a 4, an 11, an 8, and a 7 to tell us where. Okay. Pausing. I'm seeing if you have any questions for me. All right. So we have stored the program counter. Why? So we can go back. The program counter was telling us where the next line in our program is, but we're going to go someplace else and do a subroutine. We need to come back. And so that's why we need to remember what the program counter is. How do we remember things? We write them to memory. That's how we remember things. And we said that subroutines calling subroutines obeys LIFO. And so we wanted to put it in the part of memory that's known as the stack, because the stack is the part of the memory that obeys LIFO. Okay. So that was 6. We pushed the program counter onto the stack. Okay. Now, why did we do that? So we could get back. And now that we are prepared to go back, we can go over to the subroutine. And so we need to change where we are in our program. And where we are in our program is our program counter. So we just wrote down where we previously were in our program counter so that we can put something new in our program counter. That's step 7. Take the address. Remember, the subroutine, the call subroutine is in the instruction. Hence, it's in the instruction register. So this says go to subroutine A. Subroutine A is located at a particular address. So it's telling us to go to that address. So that data, the address, is part of the instruction, and it's in the instruction register, and we're taking that and putting it into PC. Okay. So part of the instruction was an address, and we're putting it into, that kind of went a little crazy there. We're putting it into, going through 12, and we're putting it into the program counter. That's going to allow us to jump to a different part of the program known as subroutine A. I forgot my arrow. I forgot my numbers down here in 6. My apologies. So that would have been, let me erase this and do it again, because I forgot my arrows. Okay, so what were we doing before? We were taking, push the value of the program counter onto the stack. So that was 4, 11, 8, and 7. Said all the numbers, but I didn't write them. 4, 11. And nobody yelled at me. I wrote them down, but I wrote them all down in the wrong place. I, of course, blame you. It's always your fault. This is why it's all wrong. Because 4 was blank. It didn't use any of the arrows other than 14. So I remembered to do it, but I did it in the wrong place. Okay. All right. Now, finally, 7. Take the address of the subroutine, which is part of the instruction, into the PC. So we're doing, here's the address part, that's a 12, and we're putting it in the program counter, which is 5. So it's at 14, 12, and a 5. Who put something onto the bus, the instruction register? Who took something off the bus, the program counter? The program counter plays an unusual role here, not its usual role of just increment and tell me where the program is, because I'm jumping around. I'm not doing my normal linear motion through a program. I'm jumping around. So the program counter's playing some unusual roles here. But so be it. All right. I'm not going to tell you the second one. I want you to try. If you want to ask me Wednesday, that's fine. If you want to ask me privately, that's fine. If you have some ideas after class and you want to ask when I finally shut up, you can hang out and ask, but I need to be asked to do the subroutine return. But again, the stack pointer, if you remember that the stack pointer's acting a lot like a program counter, and if you understood what the program counter was doing before, that gives you a lot of the sort of action that's happening. The other thing here is that this was the first time that we wrote. So we were doing 11 and 8 rather than our usual 9, 10. But the next time, we were doing a subroutine call, which is a push, which is a write. But the next time around, we're doing a return, which is a pop, which is a read. So we're not going to see 11 and 8. You're not going to see 11 and 8 in the next part. You might see 11 and 8 on the test, I don't know, but you won't see 11 and 8 on the next part because the next part involves reading, not writing. Questions for the recording? And I'll hang out for other questions. Any questions for the recording? Don't see hands up here. Well, I saw one, but it was a head scratch. I don't see chats popping up. And I think I have my speaker up so people could talk to me. They just don't like to. All right, so I'm going to stop recording. I will post this